Have you ever wondered why a simple family vacation can feel more chaotic than a corporate merger? You have conflicting schedules, mismatched budgets, and a dozen different opinions on what fun actually means. Most people see this as just stressful, unavoidable family drama. But if you're an engineer, or you're learning to think like one, you see something entirely different. You don't see chaos. You see a system with flawed inputs and a complete lack of feedback loops. You see misaligned objectives and unoptimized resource allocation. This ability to look at the messy, complicated world and see a machine underneath is not a personality quirk. It is a deliberate, structured way of thinking. It's a mental operating system that can be learned and applied to solve almost any problem you can imagine. Many videos will tell you that engineers are just good at math or that they're introverted. But that completely misses the point. It's like describing a master chef by saying they own a nice set of pans. The real magic isn't in the tools, it's in the process. In this video, we are going to deconstruct the source code of the engineering mind and give you a blueprint to run it yourself. So, what is the core programming that separates an engineer's thinking from everyone else's? It isn't about memorizing formulas or being a genius with numbers. It's a foundational mindset built on a specific set of mental models that we're going to codify today. We've distilled this complex cognitive engine into what we call the 4 pillars of engineering thinking. By understanding these pillars, you gain a universal problem-solving toolkit. First, we'll explore systems thinking, which is the art of seeing the world as an interconnected machine. Second, we'll dive into first principles decomposition, the process of tearing problems down to their fundamental truths. Third, we will master constraint-based optimization, the discipline of finding the best possible solution within real-world limits. And finally, we will cover iterative prototyping, the philosophy of failing fast to learn faster. For each pillar, I'll give you a complex engineering example and then a simple everyday example you can use today. Later in the video, I'll also give you a practical checklist that combines all 4 pillars to solve any problem step by step. This isn't just theory, it's a guide to upgrading your thinking. By the end of this video, you won't just understand how engineers think. You will have a blueprint to think like one. You'll finally have the language to explain how you see the world. So let's break that down. It starts with the first pillar, systems thinking. The foundational skill of any engineer is the ability to ignore the surface of a thing and see the system within. Systems thinking is like having X-ray vision for the hidden connections in the world. It's the ability to see any entity not as a single object, but as a collection of components, connections, and a single overarching purpose. You stop seeing a car and start seeing a propulsion system, a braking system, and an electrical system, all interacting. Let's take the complex, classic example, an aerospace engineer looking at a rocket. A layman sees a giant tube that goes up. The engineer sees a delicate dance between independent yet interconnected systems. There's the propulsion system, managing the immense forces of the fuel burn. There's the guidance system, constantly taking in data to make micro-adjustments to the trajectory. Then you have the structural system, designed to withstand extreme temperatures and pressures. And finally, the payload system, which is the entire reason the rocket exists in the first place. The engineer understands that a failure isn't just one part breaking, it's a failure of the interaction between these systems. This understanding is why they can troubleshoot problems that seem impossibly complex to others. But this thinking isn't just for rockets. Let's apply it to your morning coffee routine. You might think it's a simple task, but an engineer sees a production line. What are the inputs of this system? You have coffee beans, water, electricity, a filter, and your time. What is the process? Grinding the beans, heating the water, the brewing itself, and finally, pouring it into a mug. And a single cup of coffee, hopefully a good one. When you see it this way, you can start to identify bottlenecks and opportunities for optimization. Is grinding your beans every morning taking too long? Maybe you grind a week's worth on Sunday. Is your coffee too weak? You adjust the input ratio of beans to water. You are no longer just making coffee. You are managing a small-scale manufacturing process for a caffeinated beverage. This is the power of systems thinking. It transforms you from a passive participant into an active manager of the systems all around you. If you instinctively break down your day, your projects, or even your workouts into inputs, processes, and outputs, you're already thinking like an engineer. But it's not enough to just see the system. A true engineer has to know how to break it down. That brings us to Pillar 2, First Principles Decomposition. If systems thinking is seeing the connections, First Principles thinking is finding the indestructible bedrock of truth underneath. Most of the world reasons by analogy. We do things a certain way because that's how they've always been done, or that's how our competitor does them. First principles thinking is the disciplined process of rejecting all assumptions and deconstructing a problem down to the fundamental facts you know for sure are true. The guiding question here, popularized by thinkers from Aristotle to Elon Musk, is what are we absolutely sure is true? The most famous modern example of this is how Musk approached the cost of batteries. In the early days of SpaceX and Tesla, everyone knew batteries were incredibly expensive, around $600 per kilowatt hour. That was the market price. That was the assumption. Reasoning by analogy would mean accepting this cost and trying to make small improvements. But Musk applied first principles. He asked, what is a battery actually made of? The answer is cobalt, nickel, aluminum, carbon, some polymers, and a container. He then asked, what is the spot price for these materials on the London Metal Exchange? When he calculated the cost of buying these raw materials, the total came out to be significantly less, closer to $80 per kilowatt hour. The massive difference between $600 and $80 was just inefficiency and a lack of imagination in the manufacturing process. By starting from this bedrock of truth, he could see a path to building cheaper, more efficient batteries from scratch. This is what engineers do. They peel back the layers of how it's done to get to what it is. Now, let's bring this down to a personal level. Forget batteries and think about productivity. Many people say, I want to be more productive. Reasoning by analogy, they might buy a new planner, download a new app, or try the 5 a.m. club because someone else did. An engineer applying first principles asks, what is productivity fundamentally? The first principle of productivity is valuable output generated per unit of time invested. Okay, what are the fundamental units of that equation? You have the value of your output, the amount of time you spend, and a hidden variable, the quality of that time, which is your energy and focus. Now you have a real system to optimize. Instead of just working more, you can ask better questions. How can I increase the value of what I produce? How can I increase my focus and energy during my working hours? How can I achieve the same output in less time? You're no longer tinkering with symptoms. You're re-architecting the core equation of your effectiveness. This is the essence of first principles thinking. It replaces assumptions with truths and gives you a solid foundation to build truly innovative solutions. Now, you might think engineering is all about perfection, building the biggest, strongest, fastest thing possible. That's wrong. In fact, true engineering is about knowing when to stop. This brings us to Pillar 3, Constraint-Based Optimization. Engineers aren't paid to be perfect. They're paid to be optimally effective within constraints. This is the art of maximizing performance against a desired metric while respecting a set of fixed, real-world boundaries. Those constraints could be time, budget, the laws of physics, material strength, or computational power. Perfection is infinite, but resources are always finite. The engineer's job is to find the most elegant solution that fits inside the box of constraints. Think of the classic project management triangle, also known as the iron triangle. The three vertices are good, fast, and cheap. The rule is simple. You can pick any two. If you want it good and fast, it won't be cheap. If you want it fast and cheap, it won't be good. And if you want it good and cheap, it won't be fast. This isn't a failure. This is the fundamental nature of trade-offs. Let's take our complex example. Designing a bridge. You could theoretically design a bridge made of solid diamond that could withstand a direct asteroid impact. That would be perfect, but it would also bankrupt a small country and take a century to build. A civil engineer's task is not to build an indestructible bridge. Their job is to build a bridge that is strong enough to handle the maximum expected traffic load, plus a defined safety factor, within the city's budget and before the next election cycle. They optimize for safety and durability within the constraints of cost and time. The most elegant design is not the strongest one possible, but the most efficient one that meets all requirements. Let's look at a creative example, writing a book. An author could spend a lifetime trying to write the perfect novel, endlessly tweaking every sentence. But an author thinking like an engineer accepts their constraints. The publisher gives you a deadline of 1 year and a target word count of around 300 pages. Your job is to optimize for story clarity, character development, and pacing within that page limit and time frame. Every chapter you add means another might have to be cut or shortened. A beautifully written scene that doesn't advance the plot is inefficient. It violates the constraints. Shipping a very good book on time is infinitely better than never finishing a perfect one. This mindset is about embracing limitations as a catalyst for creativity and focus. So you have a system, you've broken it down to its core truths, and you know your constraints. Now what? You build. This leads to our final pillar, Iterative Prototyping. This pillar flips the traditional model of planning on its head. Instead of spending months or years planning in a vacuum to release a perfect final product, the engineering mindset is to build, test, learn, and repeat. This is a cyclical process of building a minimum viable version of a solution, testing it in the real world, and using the feedback as data to inform the next, slightly better version. In this world, the feedback loop is king. The core philosophy here is a radical shift in how we view failure. Don't theorize, build. Don't guess, test. Failure isn't a setback, it's data. Each failure is a data point that tells you what doesn't work, which is just as valuable as knowing what does. The classic example is modern software development using the Agile methodology. Instead of a team disappearing for 2 years to build a massive, complex piece of software, they work in short cycles called sprints. In a 2-week sprint, they might build just one new feature, the smallest, most basic version of it. This is the prototype. They release it to a small group of users and carefully measure the feedback. Do people use the feature? Do they get confused? What do they request next? This real-world data is infinitely more valuable than any internal speculation. Then, in the next sprint, they use that data to iterate on the feature, making it better, or perhaps even removing it if nobody used it. This cycle of building, measuring, and learning reduces risk and ensures that what is ultimately built is what users actually want. Let's apply this to learning a new skill, like cooking. The waterfall approach would be to read 100 cookbooks, watch 1,000 hours of cooking shows, and create the perfect kitchen setup before ever turning on the stove. The iterative engineering approach is much simpler. Pick one dish, like an omelet. That is your first prototype. Make it. It will probably be terrible. This is the test. The failure is your data. Was it too runny? Was it burnt? Did it stick to the pan? Now you iterate. Adjust one variable for the next attempt. Maybe you use lower heat, or more butter, or cook it for less time. By making a dozen terrible omelets, you learn more and faster than by just reading about 1,000 perfect ones. You are closing the feedback loop with reality, and that is the fastest path to mastery. If you are the kind of person who believes that doing something is the best way to learn it, you already have the soul of this pillar within you. If you think like this, if these pillars resonate with you, then you are in the right place. This channel is built on deconstructing the mental models of top performers, so consider subscribing to join a community of builders and thinkers. It's your turn now. Let's take these 4 powerful pillars and turn them into a practical tool you can use today. Here is the engineer's mental checklist, the tool I promised you at the start. For any problem you face, you ask yourself 4 questions. Define the system. What are the parts, connections, inputs, and outputs? 2. Find the first principles. What are the absolute, undeniable truths of this situation? Know your constraints. What are my real-world limits of time, money, and resources? 4. Plan your first iteration. What is the smallest, simplest version I can build and test right now? Let's apply this checklist to solve the chaotic family vacation from the beginning of the video. First, define the system. The inputs are people, money, and time. The output is a successful vacation, which we'll define as everyone feels relaxed and has fun. Second, what are the first principles? The undeniable truth is that people have different definitions of fun and different budget sensitivities. Third, what are the constraints? We have a total budget of $5,000, a fixed week in August, and we know 2 people want relaxation while 2 want adventure. Fourth, what is the first iteration? Instead of booking a non-refundable trip, the prototype is a shared document where everyone lists their top 3 must-have activities that fit the budget. This simple test gives you data on what people actually value, allowing you to iterate towards a plan that optimizes for everyone's happiness within the known constraints. You've turned family chaos into a solvable, structured problem. However, this way of thinking is so powerful that it comes with its own potential bugs. The first bug is analysis paralysis, where you get so lost in defining the system and its principles that you never actually build anything. Pillar 4 is the patch for this bug. Force yourself to build a prototype, no matter how small. The second bug is poor communication with non-engineers, as you might accidentally treat people like components in a machine. The patch here is empathy, remembering to translate your logic into human terms. So we have these 4 powerful pillars, and we have a checklist to apply them. But what does it all mean? The engineering mind operates on these 4 pillars: systems thinking, first principles, constraint-based optimization, and iterative prototyping. It's how you see the machine beneath the surface of reality. It's how you find the truth when everyone else is repeating assumptions. It's how you achieve elegance within the messy boundaries of the real world. And it's how you turn failure into your most valuable teacher. It's how you turn a chaotic vacation into a well-oiled machine. This way of thinking isn't just for building bridges or writing code. It is a fundamentally creative act. It's a structured method for bringing order to chaos, clarity to complexity, and turning abstract ideas into tangible reality. It is the mindset of a builder, a creator, a problem solver. You don't just solve problems, you design systems that make problems obsolete. If you remember one thing from this video, it's this: engineering isn't a job, it's a structured method for turning chaos into clarity. If this framework resonated with you and gave you a new language for how you think, subscribe for more deep dives into the mindsets of top performers. We're building a community of people dedicated to thinking better. And for our question of the day, leave a comment with one problem, big or small, that you're going to apply the engineer's checklist to. I'd love to see how you put this into practice.